January 28, 1933, Philadelphia, Pennsylvania. The Pennsylvania Railroad Board of Directors gathered in their Market Street headquarters facing a decision that could bankrupt America's most powerful transportation company. Outside, the Great Depression had shuttered factories across the industrial Northeast. Inside, Chief Mechanical Engineer George Gibbs presented plans that would cost more than the railroad's entire annual profit. Total electrification of the main line from New York to Washington, not a modernization project, not an upgrade, a complete transformation requiring $140 million when skilled workers earned $15 per week. The board members studied financial projections that made even optimistic executives nervous. Steam locomotives had powered American railroads for a century. Coal was cheap, infrastructure was established, and maintenance procedures were proven. The Pennsylvania Railroad operated the most profitable passenger service in the world using conventional steam power. Why risk everything on unproven electric technology that European railroads were still struggling to perfect? But the numbers told a different story than tradition suggested. Steam operations through tunnels in urban areas created nightmare scenarios that cost money every single day. The Hudson River tunnels into Manhattan required ventilation systems that consumed massive amounts of power just to clear smoke from previous trains. Engine changes at both ends of electrified sections wasted hours and required duplicate locomotive fleets. The Baltimore Tunnel was even worse, forcing trains to crawl through choking smoke that delayed schedules and endangered passengers. More critically, the Pennsylvania Railroad's competitors were moving faster. The New York, New Haven, and Hartford had electrified their main line in 1907. The New York Central was planning extensive electrification for their premier routes. If the Pennsylvania Railroad fell behind in speed and service quality, their lucrative Northeast Corridor passenger traffic would evaporate to competitors who offered cleaner, faster travel. The board approved the project by a narrow margin, with several directors predicting financial disaster. The Pennsylvania Railroad would build the most extensive electrification system in America, powered by 11,000-volt alternating current that required technology no American railroad had successfully deployed at this scale. The infrastructure alone represented a staggering commitment: catenary systems, substations, signal modifications, and complete rewiring of hundreds of miles of mainline track. Then came the locomotive problem. Electric power meant nothing without machines capable of utilizing it effectively. The Pennsylvania Railroad needed locomotives that could haul heavy passenger trains at sustained high speeds while providing the acceleration necessary for frequent station stops. European electric locomotives offered some guidance, but nothing existed that could meet American requirements for power, speed, and reliability on the demanding Northeast Corridor schedules. The railroad would have to design and build their own locomotive from scratch, a machine that would either justify the massive electrification investment or prove that the entire project had been a catastrophic mistake. The Altoona testing facility became ground zero for what many Pennsylvania Railroad executives privately called the most expensive failure in company history. Throughout 1934 and 1935, prototype electric locomotives arrived for evaluation, each one revealing new problems that pushed costs higher and timelines further into uncertainty. The initial design requirements seemed straightforward until engineers attempted to make them reality. The locomotive needed to produce 4,620 horsepower continuously. It had to accelerate passenger trains weighing over 1,000 tons from station stops to 100 miles per hour smoothly. It required dynamic braking systems that could safely descend grades without burning out brake shoes. And critically, it needed to operate reliably day after day on one of the busiest railroad corridors in the world. No existing electric locomotive met even half these specifications. The Pennsylvania Railroad commissioned two competing prototypes to test different technical approaches. The EP3, styled like a traditional box cab locomotive, used proven European-style technology with electrical equipment mounted in separate compartments. The GG1 prototype employed a revolutionary streamlined design with all electrical components integrated into a single articulated body. Both machines cost far more than budgeted, and neither worked properly when first tested. The electrical systems proved nightmarishly complex. 12 traction motors had to operate in perfect synchronization, or the locomotive would tear itself apart. The 11,000-volt AC power from overhead catenary required transformation to usable voltages through equipment that generated intense heat and created maintenance access problems. Early test runs revealed that the cooling systems were inadequate, motors overheated during sustained high-speed operation, circuit breakers tripped unexpectedly. The electrical gear emitted concerning sounds that made veteran engineers nervous about catastrophic failures. Weight distribution created another crisis. The locomotives were far heavier than steam engines of equivalent power. The GG1 prototype weighed 230 tons, putting stress on track infrastructure that wasn't designed for such concentrated loads. Bridge engineers studied the designs with growing alarm, calculating that existing structures might require expensive reinforcement to handle the new locomotives. Every solution created new costs that made the electrification project's financial projections look increasingly unrealistic. Inside the Pennsylvania Railroad's executive offices, pressure mounted to cancel or drastically scale back the entire electric locomotive program. Conservative estimates suggested that each locomotive would cost $3,000 and $15,000, far exceeding the $200,000 originally budgeted. The order for the planned production fleet would require millions in unexpected capital expenditure during the depths of the Depression. Steam locomotives cost half as much and were proven reliable. Why continue throwing money at temperamental machines that might never work properly? The critics gained support throughout 1935 as prototype testing revealed problem after problem. Motor failures, electrical shorts, overheating transformers, and mechanical breakdowns made the test locomotives appear to be expensive toys rather than practical transportation equipment. When the EP3 prototype suffered a major electrical fire during a test run, several board members demanded immediate cancellation of the entire electric locomotive project. March 1935 brought the Pennsylvania Railroad to a crossroads that would determine the company's future. Chief Mechanical Engineer George Gibbs stood before the board of directors with test data that told two contradictory stories. The prototype locomotives had experienced numerous failures, yes, but they had also demonstrated capabilities that no steam locomotive could match. When they worked properly, they were spectacular. The question was whether the engineering team could solve the problems before the company ran out of money and patience. Gibbs presented a detailed analysis that focused on what the prototypes had achieved during successful test runs. The GG1's streamlined design had proven superior to the boxier EP3 in multiple critical areas. The articulated body distributed weight more evenly than conventional rigid frames. The integrated electrical equipment location actually simplified maintenance access once engineers understood the system. Most importantly, during problem-free runs, the GG1 had demonstrated acceleration and sustained high-speed performance that left conventional steam locomotives far behind. The cooling system problems had solutions. Larger ventilation fans and improved airflow design could handle the heat generation from sustained operation. The electrical issues traced to component quality rather than fundamental design flaws. Better circuit breakers, improved motor insulation, and refined transformer specifications would address the reliability concerns. The fixes would cost money, but they weren't impossible. The Pennsylvania Railroad could build reliable electric locomotives if they committed to solving the identified problems. The competition factor weighed heavily in the final decision. While the Pennsylvania Railroad struggled with prototype problems, other railroads were making progress with electric operations. The New Haven Railroad's electric locomotives were handling passenger service successfully. European railways continued advancing their technology. If the Pennsylvania Railroad abandoned electrification now, they would fall permanently behind competitors in the crucial Northeast Corridor market. The hundreds of millions already invested in catenary and power distribution would become a monument to failure rather than the foundation for modern operations. The board made their decision in April 1935. The Pennsylvania Railroad would order a production fleet of GG1 locomotives incorporating all the improvements identified during prototype testing. The initial order specified 57 units at a revised cost of $315,000 each. Additional modifications to electrical equipment, cooling systems, and mechanical components pushed total development costs even higher. The financial commitment was enormous, and failure would likely trigger the resignation of every executive who supported the decision. The production contract went to General Electric and the Pennsylvania Railroad's own Altoona shops, working in collaboration. GE would manufacture the electrical components while Altoona handled mechanical assembly and final integration. The partnership arrangement theoretically combined GE's electrical expertise with the railroad's understanding of operational requirements. In practice, it created coordination challenges that delayed deliveries and increased costs as the two organizations struggled to synchronize their efforts. The first production GG1 number 4800 emerged from Altoona in August 1935. The locomotive incorporated hundreds of modifications based on prototype testing experience. Improved cooling fans, upgraded electrical insulation, refined motor controls, and strengthened mechanical components. The machine looked identical to the prototype from outside, but internal improvements represented millions in additional engineering work. Now came the ultimate test. Would the production locomotives prove that the Pennsylvania Railroad's faith and investment had been justified, or would they demonstrate that some problems simply couldn't be engineered away? January 28, 1936. The first production GG1 departed Philadelphia's 30th Street station, hauling the Congressional Limited toward New York. Veteran locomotive engineers accustomed to steam power were about to discover what properly designed electric traction could accomplish. The acceleration from the platform left passengers pressed back in their seats as the streamlined locomotive pulled away with authority that no steam engine could match. Within minutes, the train reached cruising speed, and the GG1 settled into the steady high-speed running that would become its trademark. The performance metrics exceeded even optimistic projections. The GG1 accelerated the 1-meson-ton train from 0 to 100 miles per hour in under 5 minutes. Steam locomotives required twice that time and significantly more distance. More importantly, the electric locomotive maintained maximum speed effortlessly on grades that forced steam engines to slow down. The continuous power delivery meant schedules could be maintained regardless of track conditions or weather that hampered conventional operations. The reliability that had seemed impossible during prototype testing materialized once production locomotives entered regular service. The engineering improvements made during development had solved the critical problems. Cooling systems handled sustained high-speed operation without overheating. Electrical components operated within specifications day after day. The locomotives ran scheduled assignments without the failures that had plagued prototypes. Engineers reported that the GG1s simply worked, delivering consistent performance that allowed maintenance crews to establish predictable service intervals. The operational advantages became obvious within weeks of GG1 deployment. Tunnel operations that had required slow speeds and extensive ventilation under steam power became routine at normal track speed. The elimination of smoke cleared sight lines and improved safety. Station stops no longer filled platforms with coal smoke and cinders that drove passengers away. The clean, quiet electric operation transformed passenger experience in the ways that marketing departments immediately recognized as competitive advantages. More significantly for railroad finances, the operational efficiency delivered cost savings that finally justified the massive electrification investment. A single GG1 could handle assignments that required 2 steam locomotives and frequent water stops. The elimination of coal handling infrastructure saved millions annually. Reduced maintenance requirements meant locomotives spent more time in revenue service and less time in shops. The Pennsylvania Railroad began calculating that electrification would achieve positive return on investment faster than even optimistic projections had suggested. Passenger reaction provided unexpected validation. Travelers who chose trains based on speed and comfort began specifically requesting GG1 hauled services. The smooth acceleration, vibration-free high-speed running, and absence of coal smoke created a premium travel experience that competed favorably with automobile and air travel. The Pennsylvania Railroad's passenger traffic actually increased during a period when most railroads were losing customers to competing transportation modes. By the end of 1936, the GG1 had proven itself beyond any doubt. The Pennsylvania Railroad ordered additional locomotives to expand electric operations. The machines that critics had called expensive failures were generating profits through superior performance and reliability. The engineering team had taken a nearly disastrous prototype and transformed it into a locomotive that exceeded every specification that mattered for practical railroad operations. The gamble that could have bankrupted the Pennsylvania Railroad was paying off. The 1940s brought new electric locomotive designs that promised to make the GG1 obsolete. Competitors and even Pennsylvania Railroad engineers developed supposedly superior alternatives that incorporated advancing technology and lessons learned from GG1 operations. Streamlined diesels entered service, with manufacturers claiming they offered electric locomotive performance without catenary infrastructure costs. More powerful electric designs emerged from other railroads pursuing their own electrification programs. Each new challenger would supposedly surpass the aging GG1 design and prove that the Pennsylvania Railroad needed to modernize their fleet. The New Haven Railroad's EP5 class locomotives represented the most serious American competition. Introduced in 1955, these streamlined electrics featured mercury arc rectifiers and advanced electrical systems that provided more power from lighter machines. The specifications impressed technical journals, and New Haven engineers confidently predicted their locomotives would demonstrate clear superiority over the outdated GG1 design. Initial performance seemed to validate their claims, with the EP5s delivering excellent acceleration and high-speed capability. But superior specifications didn't translate to superior operational reliability. The EP5 locomotives suffered from the same problems that had plagued earlier attempts to improve on proven designs. Mercury arc rectifiers were temperamental and required specialized maintenance expertise. The lighter construction that reduced initial costs also reduced durability under sustained heavy service. Within a decade, the New Haven was struggling with expensive repairs and premature overhauls, while Pennsylvania Railroad GG1s continued running their original assignments with routine maintenance. Diesel-electric locomotives presented a different challenge. By the 1950s, EMD and other manufacturers were producing powerful road diesels that eliminated catenary infrastructure requirements while promising operating costs comparable to electric traction. The Pennsylvania Railroad tested diesels extensively on non-electrified routes and seriously considered expanding diesel operations at the expense of electric service. The diesels worked well enough in many applications, but they couldn't match GG1 performance on the demanding Northeast Corridor schedules. The fundamental advantages that made the GG1 design successful in the 1930s remained relevant decades later. The articulated body distributed weight efficiently and handled track irregularities better than rigid frames. The simple mechanical design meant repairs could be completed quickly without extensive downtime. The robust electrical systems, built with conservative specifications and quality components, outlasted equipment designed to minimize initial costs. Most importantly, the locomotives simply kept working year after year without the major failures that sidelined supposedly superior alternatives. The Pennsylvania Railroad's own attempts to replace the GG1 demonstrated just how difficult it was to improve on the original design. Company engineers developed plans for next-generation electric locomotives, incorporating modern technology and addressing perceived GG1 limitations. Prototypes were built and tested. None delivered enough practical advantage to justify replacing locomotives that were still performing perfectly after decades of intensive service. The engineering team had gotten it right the first time, and subsequent refinements couldn't produce meaningful improvements. By the 1960s, railroad industry observers recognized the GG1 phenomenon as something unusual in a business that constantly pursued newer technology. Here was a locomotive designed in the mid-1930s that was still the most reliable, most practical, most cost-effective machine for its intended service 3 decades later. Everything that was supposed to make it obsolete had instead proven inferior when subjected to the same demanding operational conditions. The locomotive that nearly destroyed the Pennsylvania Railroad had become the standard against which every alternative was measured and found wanting. The Pennsylvania Railroad's Northeast Corridor represented the most demanding railroad operation in America. Between New York and Washington, passenger trains ran at frequencies that approached subway service during peak hours. Freight moved through constantly, fitting around passenger schedules that couldn't be delayed. Track maintenance required precise coordination to avoid disrupting revenue service. The GG1 fleet became the foundation that made this intense operation possible. handling assignments that would have been impossible with any other motive power. The locomotive's ability to maintain precise schedules proved critical for corridor operations. Unlike steam power that required water stops and coal servicing that interrupted tight timetables, the GG1s ran continuously between major terminals with only minimal attention. The reliable acceleration meant trains recovered quickly from station stops without cascading delays. The sustained high-speed capability allowed express runs to maintain advertised times even when track work or signal delays created complications. Dispatchers learned they could depend on GG1 performance in ways that no previous locomotive permitted. Passenger service quality depended entirely on GG1 reliability during the railroad's peak years. The Metroliner service introduced in 1969 pushed speeds above 100 miles per hour on upgraded track, but GG1 locomotives still handled the premium trains that generated the most revenue. Business travelers who needed dependable transportation between major Northeast cities chose Pennsylvania Railroad trains specifically because GG1 operations delivered consistent, on-time performance. When locomotives failed, passenger revenue suffered immediately and visibly. The freight operations that kept the Pennsylvania Railroad profitable relied on GG1 locomotives for time-sensitive shipments. Mail trains ran on passenger schedules, requiring the same speed and reliability that passenger service demanded. Perishable freight moved quickly through the corridor without the delays that steam operations imposed. The ability to handle both passenger and freight assignments meant the Pennsylvania Railroad could maximize catenary infrastructure utilization and justify the continuing costs of electric operations even as other railroads abandoned electrification. Maintenance efficiency became a critical factor in the locomotive's operational success. The Pennsylvania Railroad developed systematic procedures that maximized GG1 availability while minimizing shop time. Routine inspections caught potential problems before they caused failures. Component replacement schedules based on actual service experience prevented premature wear while avoiding unnecessary preventive work. The result was a fleet that consistently delivered 85 to 90% availability, far exceeding typical railroad motive power performance. The economic impact extended beyond direct operational costs. The Pennsylvania Railroad's ability to maintain competitive passenger service while other railroads surrendered to highway and air competition depended fundamentally on GG1 capabilities. The locomotives enabled the railroad to offer travel times and service frequency that justified premium fares. Business travelers paid extra for reliable Northeast Corridor trains when competitive modes couldn't guarantee on-time arrival. The revenue premium from GG1 hauled premier services helped sustain the railroad's financial viability through challenging economic periods. By the 1970s, the GG1 fleet had become so integral to Northeast Corridor operations that railroad planners couldn't imagine running without them. Replacement discussions focused on finding locomotives that could match GG1 reliability, rather than simply pursuing superior specifications. The machines that had nearly bankrupted the Pennsylvania Railroad 4 decades earlier had become the irreplaceable foundation of America's most important passenger rail corridor. The railroad's survival depended on locomotives that just kept working year after year, delivering the consistent performance that made passenger rail service viable in an era when most railroads had abandoned the business entirely. October 1968 brought the merger that created Penn Central, combining the Pennsylvania Railroad and New York Central into what would become the largest corporate bankruptcy in American history. The new railroad inherited massive debt, redundant infrastructure, and operational chaos that would destroy it within 2 years. But among the wreckage of failed management and incompatible systems, one asset continued performing exactly as designed. The GG1 fleet kept running Northeast Corridor passenger trains through bankruptcy, through the creation of Amtrak, through railroad reorganizations that eliminated the Pennsylvania Railroad's very existence. When Amtrak assumed responsibility for intercity passenger service in 1971, the GG1 locomotives were already approaching 40 years of continuous operation. Conventional railroad wisdom suggested that motive power this old should be ready for retirement and replacement with modern equipment. But Amtrak discovered what Pennsylvania Railroad engineers had known for decades: The GG1s were still the most reliable, most practical locomotives available for Northeast Corridor service. The new railroad had no choice but to continue depending on machines designed during the Great Depression to carry passengers in the 1970s. The final years of GG1 operations demonstrated both the design's fundamental soundness and the inevitable limitations of even the best mechanical equipment. By the early 1980s, finding replacement parts had become increasingly difficult as suppliers disappeared and manufacturing specifications became obsolete. The electrical components built with 1930s technology couldn't be easily replaced with modern equivalents that didn't match original designs. Maintenance costs rose as mechanics spent more time fabricating custom parts and solving problems that reflected 5 decades of accumulated wear. The decision to retire the GG1 fleet came not from operational failure, but from practical impossibility of continuing support. The last locomotives left regular service in October 1983, nearly 50 years after the first production unit entered operation. No other American electric locomotive came close to this service longevity. The Swedish-built AEM-7 locomotives that replaced them were fine machines, but they would be retired after 30 years, proving that modern engineering still hadn't matched the durability of 1930s Pennsylvania Railroad design standards. The historical verdict on the GG1 transformed completely from the skepticism that nearly killed the project before production began. Railroad historians recognize the locomotive as one of the most successful designs in American rail history. The machine that critics called too expensive and too risky had delivered 5 decades of reliable service, outlasting the railroad that built it and validating every dollar of the massive investment that frightened executives in 1933. The Pennsylvania Railroad's gamble on electric traction had paid off beyond any reasonable expectation. More significantly, the GG1 demonstrated principles that remained relevant for modern transportation engineering. Conservative design standards produce longevity that offset higher initial costs. Simple, robust mechanical systems outlasted sophisticated alternatives that looked more advanced, but failed more frequently. Quality manufacturing and materials generated reliability that justified premium prices. The lessons learned from 1930s electric locomotive development remained applicable to 21st century transportation challenges, where engineering decisions still balanced initial investment against lifetime performance. The GG1s that survived retirement found homes in museums across America, preserved as monuments to engineering excellence and railroad history. But their true legacy lived in the Northeast Corridor operations they made possible. The passenger rail service that connects Washington, Philadelphia, New York, and Boston exists because the Pennsylvania Railroad succeeded with electrification in the 1930s. The GG1 locomotives justified that investment through decades of superior performance, proving that sometimes the machines that nearly destroy their creators become the innovations that define entire industries. The locomotive sketched in desperation during the Great Depression had saved American passenger rail service in the Northeast, outlasting predictions, exceeding expectations, and demonstrating that properly engineered solutions can work perfectly for half a century, exactly as designed.